Hello and welcome to today's webinar on full vehicle analysis for Formula SAE with Adam's car. Our presenter is Anirudh Matanj, and he goes by Ani. He joined Hexagon at the start of 2018 and is based at the Novi office near Detroit. He is part of our Adams Consulting Services team and helps customers with modeling, methods development, custom GUI development, simulation, analysis, and design optimization. He uses Adam's car and Adam's view. And I think that one of the reasons why he's a very credible speaker today for this webinar is that he was the suspension lead at the University of Texas, Arlington, leading to his team placing 5th overall in FSAE Lincoln and 8th in FS UK, both in 2018. He had previously told me that he had used Adam's car for that after he had designed the suspension, and then they fabricated it and compared. His advisor was really shocked by how tight the agreement was between Adams and real life. Ani, I'm really looking forward to your talk today, which is going to be building on, in some ways, last week's talk that was focused on just this suspension. It'll be great to see the actual full vehicle operating. So thank you. I'm ready to hear from you.
Thanks, Alex. Hi, guys. Ani here. Like Alex said, I was an ex-FSAE student, and our team did reasonably well, I would say. So today, what I would like to show you guys is how, once you guys have set up the suspension and all your kinematics and compliances and all of that stuff is done, how you should sort of set up your full vehicle model. And we will start first with what is the difference between a full vehicle model and the suspension model or the suspension assembly. And if you see here, essentially, these are the things that you need for a suspension assembly. You just need just a suspension subsystem. If it's a front subsystem, obviously you'll need the steering. And if you have ARBs or anything else, that goes in the other side. And of course, it connects to the suspension test rig. On the other hand, you have the full vehicle assembly, which of course, just like in a real car, you need the engine, you need the chassis, you need the brakes and all of that stuff. So all of those have to be, you need the wheels, obviously. So you need to include all of those things. And again, in the other, you can plug in the aero or the ARBs and everything else. And then, of course, there is the test rig, which is obviously different from the suspension test rig. And it is the SDI test rig, or what we call the standard driver interface. And that's the sort of like the stuff that you need to set up your full vehicle model. But now let me go back and talk a little bit about what we're going to do for the rest of the, I don't know, 30 to 45 minutes that we're going to be talking about Adams today. Here's what we're going to talk about, what the full vehicle assembly is and how it differs from the suspension assembly, what all you need. And that's what I just showed you guys. Then how to set up the model. And then, of course, how a standard, how to do one iteration of your design so that, just giving you a look at how you should go about running simulations and then figuring out what to do after you've looked at the plots and other metrics from the simulation. So let's talk a little bit about Adams also, since that's the main topic of interest here. The Adams is, well, the boring version is that it stands for Automatic Dynamic Analysis of Mechanical Systems. That's ADAMS. It is now 50 years old. It turned 50 this year, actually. And it started as just a research project at the University of Michigan in Ann Arbor. It is the most advanced. It can do all the tricks when it comes to multi-body dynamics. It can do your KNC analysis. It can do full vehicle dynamic analysis. You can co-simulate with MATLAB or import FMUs that have the control systems that you guys might be including in your vehicle. And then, of course, if you have access to a simulator, you can actually just take your actual Adams model and connect it directly to the simulator and drive it around in that simulator. So I think there are, of course, a lot of other MBD tools out there, but not all of them can do all of these things. Some of them are specialized for certain things, others are specialized for other things, but Atoms is one of those which can essentially do all of those, all of the above. So we talked about the difference between a full vehicle assembly and a suspension assembly, what you need, what you don't need, and how to kind of create or sort of set it up. Then we will be talking about these few things, which is how to set up the body subsystem, how to set up the brake subsystem, and how to set up the powertrain subsystem, so that the performance, general performance that you get from these, or is at least somewhat close to what you have on your real vehicle. So let's start with that. So the premise is that you guys have your KNC and your suspensions fully set up, and now you just want to go into doing full vehicle dynamic analysis. So here I've opened the default of FSAE full vehicle assembly, and I am going to show you how to set up the body first. Now, the first thing is you obviously want to make sure that all of your bits and pieces are of the correct mass and inertia, which is like the A-arms, the tie rod, the rack, the steering, the bits of the steering column, all of that stuff. You want all of that to be the correct numbers, which you get from your CAD, or maybe, like the dampers, etc. You have the weight. You can just, weigh it on a machine and plug those numbers in and estimate some inertia for that. Once all of that is in, which means all of your parts are the correct amount of mass and inertia, it means that all that's left is to include the chassis and all of the wires and all of other stuff that's in the on the car, but obviously you can't really model that in Atoms. So you still want to include that in there. So the first thing you do is you go to setup, you go to model info, and you go to aggregate mass. You go to select all so that you get that mass and inertia of the whole vehicle. You hit apply. Now there are multiple different reference systems and things like that, but the one that I want you to focus on is the last one. This one says here's now it tells us that the mass of the vehicle is 265 kilos, and the COG is located here, and the mass and inertia are this much. Let me zoom in so maybe you guys can see better. So, and the most important one, so to speak, or the easiest one to work with is the mass inertia tensor that is about the center of mass, but is oriented with the global XYZ coordinates so that, you don't have to transform things again and again to get the right numbers. So what we're going to do is we're going to copy this whole thing into Excel. One other thing that I'm trying to show you here is how useful Excel is for when you're using Atoms. So you just paste it, you go to data. I'm sure you guys have done this before. You go to text to columns, you delimit it, and you separate them out. So that's done. So now this is the amount of inertia that the vehicle has right now. However, and let's say mass, it said was 265.18. I'll just call it for now, just to make life easier. So let's say your actual vehicle mass, I'm just going to multiply all these numbers by 1.2, just because we are just doing this first demonstration. So let's say that everything is going to be 1.2 times this number. And the other thing that we know about the vehicle is that you guys have a 45:55 ratio for, that means that 45% of the mass is in the front, which means it's this amount of force on the front axle, which means assuming that your car is perfectly symmetric, this means that your front left and front right tires should roughly have this amount of normal force that they're supporting. That is the information we have from all the other Excel sheets that you might have set up for doing the initial setup for your suspension. So this is what we want to do. We want to make sure that the inertias are this much, the mass is this much, and that the COG is located in such a way that you get 585 newtons of force on the front left and the front right tires. So how are we going to do that? First we'll work on just the mass. We will go to the chassis mass, and we are just simply going to add the leftover, which is this. It's 53.06. Copy, paste values. I'm just doing this because I know otherwise it also, when I paste into the into Adams, it'll also include the tab. So I don't want that. I just want the text, which is 53.06. I take that. I can just say plus 53.06, hit apply, and now the new mass will be updated, as you can see. And I hit apply again on the aggregate mass, and now you can see that the vehicle now weighs 318 kilos. Obviously, these numbers have also changed. You can see that they have changed a little bit, not a lot, but a little bit. Obviously, only 50 kilograms, which is not a huge amount. And now what we're going to do is, since this is the new inertia tensor, we'll copy that again, paste it, do the same data to text stuff. So now this is the new stuff. And I'm going to say this minus this, which gives me all of the remaining stuff. Now you can see that this is like E minus 5, so I'm just going to ignore this since it's very small. And I'm going to turn off the diagonal terms. And now we're going to add these numbers here. The numbers that you see here, I'm just going to start plugging them in. Plus 5.46 E6 plus 1.73 E7 plus 1.87 E7. And then I'm going to hit apply. Things do have a tendency of disappearing behind windows in Adams. But that's just part and parcel. So now you can see that the inertia tensor has updated, and now we're going to compare the numbers. So you can see here it's 3.28, which is what it is here, the first three digits. 1.04, 1.0366, pretty close. 1.12, it's 1.12. So now your inertia of your vehicle is correct. Now we're going to adjust the COG. So to adjust the COG, what we will do is we will run a simulation called the SVC, which is under full vehicle, static and quasi-static maneuvers, and then static vehicle characteristics. Hit this individual part. You can give it whatever name you. Oh, before you do that, go to select directory. And so the default directory is always your whatever your username location is. I like to place my things in a very organized manner. As you can see, there's so many things over there. So I have a special folder specifically for the FSA tutorial. I would suggest that you guys also have some sort of setup to organize your files, because otherwise it can get very, very hairy and you can basically lose your information. So I'm going to hit apply. It ran the simulation. Now it's telling me that the front ground reaction is 766, and also you can see that this car is almost perfectly balanced at 50-50 here. 766, 793, that's not a huge difference. But what we want is this number to be 585, which means we need to shift the weight backwards. And that's what I'm going to do here. I just like to keep things in this location, not something that it doesn't really matter, but just a matter of preference. So now we need to shift this. Let's say I'll shift this by 25 mm. And then I'll run this again. So now you can see some of the weight has shifted back, but the difference is not a lot. It was like 760. It only changed by about 5 kilos on each side. So we need to remove about 160, which means we'll have to shift this back quite a bit. So let's say even 400 mm. So now we're getting closer. Still not there yet. 665, maybe another 100 mm. Hopefully this will be enough or close enough. All right, 585. That's as close as I like for now. So now your front to rear weight balance is ready. It's where it should be. So what you should do is you should save your, I'm not going to do this, but you should save your subsystem, which is the body subsystem. Where is it? Chassis. So you can save this. And then all the new stuff is saved away and you don't have to touch it after this. The next thing that we're going to work on is the brakes. Now, I'm also going to show you how to do this without like wasting too much time. So just touch the things that need to be updated to get what you need. So what we're going to do is go to the parameter variables, go to the table, and switch to the brake system. Now there's a lot of parameter variables here, but the only ones that you need to worry about are the brake bias, the brake mu, and the piston radius and piston area. All the others are actually just graphical things, and they just change the graphics of what you see here, this caliper-like or rotor-like thing and all that kind of stuff. So you don't have to worry about that. Just worry about these four things and these four things. And what essentially you need to do is run a straight line braking maneuver. So simulate full vehicle straight line events braking. I'm just going to give it in, let's say, 5 seconds, 500. A good step size to use for in general is 0.01. Sometimes you might need to go finer if there's a lot of dynamic stuff happening in the model. So you need to, be solve at smaller time intervals. And I'm going to say, let's slow down from 100 just so that I have enough time to see how things are going. Obviously, I wanted to keep in a straight line. I'll start at 1 second. I will apply full brakes in over the duration of 1 second. And I will hit apply. So unfortunately, I chose the wrong velocity. Obviously, the vehicle cannot do 1,000 kilometers an hour. And I had to obviously run it at a more reasonable speed to get the right, actual answer, you could say. And now what we're going to do is we're just going to look at the chassis acceleration. So I'll filter it by chassis since that's enough for me to get these particular requests that I'm looking for. I will go into the accelerations and I will plot the longitudinal acceleration. Obviously, it should be hard braking. So as you can see here, the maximum braking that you have achieved is about 1G. Now, you guys will have to decide according to whatever is your brake setup, and then change the numbers that I showed you here. The brake bias, the brake mu, the effective piston radius, and the piston area. If you move these around, then of course, the brake bias will shift the torque from front to back, the ratio from front to back, and then of course, these three control how much friction is generated at the calipers for front and rear. So you adjust them and get the right amount. The other thing that you guys can also look at if you don't want to look at G's is the brake torques. You go to so you can see that there are 4 brake torques because there are four wheels, so there's 4 brakes, so there's 4 brake torques, and you can plot the torques instead. And then you can, if you'd like, you can choose these and like tune for how much brake torque is applied at each wheel instead. So either way is fine, whichever works better for you. You just need to get the correct braking performance. So now let's assume that now we have the brakes. You can change these numbers and figure that out. And we can say that the brakes are ready and doing the thing that they should do in real life. The next is the engine. Now for the engine, you go to setup, full vehicle assembly, and you go to powertrain parameters. Of course, now some of you might be using EV powertrains, and we do have a separate motor model that you might want to use, but it is a little bit complicated. You will have to work a little bit extra to get it to work, not to work, but to do what you would like it to do, which is why I'm just sticking to the regular IC engine thing here. And if you guys have your full, like, you have your power map and you know exactly all your gear ratios, which mostly obviously you should, then you can go to the gears, you can set up your ratios, you can set up the downshift RPM that you think you guys are going to have and the upshift RPM as well. So then essentially the software will upshift at or downshift at the right RPMs. And of course, you'll get the correct torque and power from the engine. You can also, once you've done all of this, you can also look at the power and velocity plots and make sure that they make sense according to what your engine or motor can do. And here, of course, it says it looks like this thing can make 430 horsepower, which is obviously not very useful for you guys at FSAE. So you'll have to create your own engine map. I'm going to show you an example of the engine map that is slightly better, which is this one. So here you can see that essentially what they do is these are the throttle values, and the number of throttle values you see here, that's how many columns you need to have over here. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. On the left side is the RPM. So obviously that's the engine RPM, but you see 1, 2, 3, 4, 5, 6, 7, 8, and 9 columns each for one of these throttle values. And just open it up, put the correct numbers in for the torque, and obviously your engine RPMs go in the first column. And depending on if you do want if you have different kind of inputs at different throttle values, you can plug that in here to kind of map that as well. But you can also leave it just at 0 and 1 and just have 2 columns like you saw in the previous version of this file. Here you see that there's only 2 columns. One is for 0 throttle, the other one is for full throttle. So you do that, and then what you want to do is you want to run the straight line event called acceleration, and you want to see how fast you can go. I'm going to do the exact same thing as I did with brakes. Instead of, obviously, I'm going to start not at 100, but at 10. One more thing that I want to talk about before I start the simulation is that if you want to do your electric motors in a super easy way, what you can do is switch it to simple proportional torque, and then just provide, here you can provide your region braking torque, how much the motor will absorb when you're braking, and then at torque, this is your maximum torque of the output from the motor, and this is the maximum power of the motor. That way it won't exactly be like a motor because you won't get full torque throughout the RPM, which the motor can do, but at least it'll be a little bit closer. So once I'm done with this, I'm gonna just go back to this one. I'm gonna change this because I do have a power map from when I was doing FSAE. So that is a little bit more representative. Oops. And in this case, I guess you actually get to find out how fast your car can accelerate. So again, go back to chassis accelerations and plot the longitudinal acceleration. As you can see, this is in G's. So it's speeding up as we go. So now you guys essentially have a model that is correctly set up for, in general, dynamic maneuvers. Your brakes are doing what they're supposed to do. Your engine it does have the correct power and torque curves, and your weight balance is correct. So now you go to the next step of actually running some sort of dynamic analysis. In this case, we're gonna do a simple skid pad, and I'll show you why or how we're gonna do that. So I do want to talk about what I'm going to do here, which is called a design iteration. Essentially, you have your initial vehicle setup that you start with. Let's say it's got the initial suspension geometry. You have your spring and damper curves. You have your initial static toe and camber settings. Then you adjust one of those or multiple one of those, and you run the simulation. You see what the numbers come out to be, whatever metrics you're trying to capture, whether that's bump steer, camber change, understeer gradient, roll gradient, whatever that might be. Then you change one of those parameters. Maybe you change the stiffness of the spring, or you switch to a different type damper curve or something like that. And then you rerun that simulation, and you compare the metrics between the two. And then you say, okay, I wanted it to go this way or that way, so I should do something about the inputs that I changed and change those in a different way so that it actually the performance shifts to the direction that you want it to. And what I've also created an example for this, which is, again, you run a skid pads, which is what we're going to do. We will change the hard points that are the lower ball joint of the front of both suspensions and the tie rod, both inner and outer points for the tie rod. I know that these are going to affect the understeer gradient, which is why I've selected those. And then I'm going to plot the understeer gradient, and then I'm going to do that for like two or three different versions of those hard points, and then we'll see what happens. How do you select your inputs to the simulation? So we're going to be doing the FSA skidpad, which we know from their information that the skidpad radius is 7125 mm. We know that our track width is roughly around 1250, give or take, depending on how you guys have set up your suspensions. So it's plus 625, and we'll give, since we don't have Max Verstappen driving our car, we'll give the driver about 100 mm of margin or clearance so that he can clear the course without hitting any of the cones. So the total radius of our turn would be 8350 or 8.35 meters. So which is what I've put over here, 8.35 meters, and step size, again, like I said before, will be 1e minus 2 or 0.01. I know that I would like to see my car go from X amount of lateral Gs to Y, which is something that you would have targeted when setting up your suspension and like knowing your tire performance and all of that stuff. So let's say in this case, I know that the default FSA vehicle is not able to do 1.5 Gs. So I'm only going to go up to 1.1 Gs. One other thing that I want you guys to notice is the amount of time I'm giving the maneuver. You don't want it to be too short, because then there'll be a lot of dynamics. This is supposed to be constant radius, some sort of steady cornering. So you want it to be slow enough that you're not inducing any excessive transients. So what I do essentially is give it 2 seconds per 0.1 G of acceleration. So you can see that the difference is 1 G, and I'm giving it 20 seconds to perform the maneuver. So now going back here, I go to simulate, full vehicle, cornering events, constant radius cornering. And then I will just call it iteration 1. Gear position, maybe 2, 8.35, 20 seconds. I want it to do lateral acceleration, and my final limit is 1.1. So I'm going to hit apply, and it's going to run the simulation. Now I'm going to adjust my hard points, which is my lower ball joint. It's at 122. This is just a demonstration, so I'm just going to make it 130. And then tie rod inner and outer are at 172. Both are at the same height, so I'm just going to make this 175, and I'm going to make this 165. And I'm going to say iteration 2, and I'm going to just simply rerun the simulation. Both simulations are now complete. I go back to the post processor. I don't need this page. I select both of the simulations together. I hit the data tab. I go to accelerations. I want to plot steering wheel angle versus lateral acceleration. So the thing that you're selecting here is the x-axis of the plot. And then I go to my condition sensors, as they're called in Adam's car. I pick them, I scroll all the way to the bottom, and then there is steering wheel angle. So plot these, as you can see here. So you can manipulate the curves through this math tab here. I can do any kind of different kind of manipulation. So I'm going to just multiply that by -1 so that the lateral acceleration is just positive. And according to the default conventions that are followed everywhere. And so here you can see that after I changed the hard points, the curve completely shifted and the overall slope changed by a certain amount. Like, of course, this will all depend on how you want it to change, which way you want it to go. Do you want it to be flat? Do you want it to understeer, oversteer, whatever you guys would like. And then, so now that I see that it has done this, I can say, okay, I didn't want that to happen. What if I do it the other way around for the tie rods? I switch it up. I flip them the other way. and I'm going to do iteration 3, and I'm going to plug. Now, of course, since I manipulated these two, I'm not going to select all of them again. I'll just select number 3, add it to the plot, and then I'll do the same lateral acceleration manipulation that I did before. And you can see that now, of course, since I flipped it, it went the other way. So now you know that if you do this to the tie rod points, the understeer curve shifts this way. So now you know exactly how the relationship it is between those two, and then you can adjust it the way you want to adjust it. And with that, my webinar is done, and I will pass it on to Alex for the last bit.
So I'd like to tell you about next steps with Hexagon. You can access our student competition bundle at the link shown on the screen. With the student competition bundle, you can access a variety of our software, including Adam's car, and these are the full commercial releases. There is some overhead in getting the competition bundle. It is simpler to apply for the free student editions. Again, either of those options is totally free, but the student editions have limited model size. And for Adams, you can only do Adams View, which is the general interface, not Adams car. So if you wanted to do this exact activity, you should apply for the student competition bundle. But if you want to get started with Hexagon software, you can apply this afternoon for the student edition. We have more webinars in this series. Coming up next week is finite element analysis with MSc Apex and MSc Nastran. I will be presenting that. And then we'll have another webinar rounding things out with Adam's car in 2 weeks. Note that that one will actually be on a Tuesday. Most of these webinars are on Wednesdays. And we have a webinar homepage where you can keep up. You can find our YouTube recordings of the videos, supplemental files, model files, slides, that kind of thing. And you can simply follow MSc Software Hexagon on YouTube to see recordings of these webinars. I know that if you're attending live, it can help to go back and watch the video as you work through the exercise yourself. And you can keep up with us on LinkedIn. With that, I think that we are ready for questions.
So I think our team had problems previously because our suspension's inboard, and there were problems with modeling that. So I'm not sure it works on like the rocker tubes are shared between the roll spring and the heave spring, and the roll spring only ever acts in compression rather than, if you've seen the Multimatic ones for FS, they act in compression and extension. So I think they're easier to model, but I haven't had a look at it myself. I was just wondering if this is something that's like.
I mean, it should be possible. It's a matter of like setting up the constraints correctly. And I mean, if you like, you have to look at the picture of whatever you have, the mechanism that you have designed, and then like set up the constraints accordingly. I mean, I don't think that it's not possible. Adams is like essentially like a Lego set, so you can plug things in the correct order, and then they'll work.
Okay, sounds good. Thank you.
Ani, do you have any tips that you wish that somebody had told you about Adam's car for Formula when you were starting out that you haven't already mentioned today?
I guess the most important thing that I learned was how to like keep my the folder structure that I sort of created for myself so that I could organize my files and things. That is something that usually isn't done when you're in college. You're pretty chaotic. Your life is chaotic and stuff. But if you have a good folder structure, that can really make life easier later on to find things, in just general organization also, so that if you're gone and somebody else needs to take up after you, they know where to find things.
Yeah, I would agree with that. And I would say that the folder structure for Adam's car is particularly complex. It is more complex than what I see for a lot of other Hexagon products, and you really have to work with it. You can't just move things around or rename a folder and expect it to work fine. And a lot of the reason for that is, unlike a lot of other simulation software, an Adam's car model is going to be touched not just by a handful of different people, but in industry it will be touched by a handful of different groups. And so being able to control access to the model is really critical for being able to keep it reasonable. Because Adam's car is really optimized for the automotive industry, it is a little bit higher powered than you need for a lot of Formula SAE activities. And at the same time, I think that if you accept the folder structure for what it is and work with it, you're going to be totally fine. And if you can wrap your mind around it, that makes you more employable too. I think another thing that is really important conceptually is to just accept the hierarchy between assemblies, subsystems, and parts, and to work with the limitations that Atom's templating system uses in Atom's car so that you can control your design and keep it really well organized. Ani, thank you so much for presenting. I found it really helpful to see a full workflow with Atom's car for the full vehicle. I hope that that was really helpful for the people who attended today and people who will be watching later on YouTube.
Thanks, everybody.
Okay, have a great day, everyone. Bye.